Good morning, everyone. I'm Honn Kao, project leader of the Induced Seismicity Research Project, Environmental Geoscience Program. In this talk, I will very briefly introduce some highlights of what we have accomplished in the year of 2021 to 22. This presentation will be made available at NRCan's GeoScan database, and this slide shows the related information. The Induced Seismicity Research Project has a national scope with members from 3 different offices. The project has established close collaboration with both public and private sectors to address critical knowledge gaps in the study of induced events and to provide observation-based science to improve regulation on the development of unconventional hydrocarbon resources. Key accomplishments that we have established for the past year include compilation of induced events catalog for Western Canada, publication of research results on the source characteristics of significant events in Canada, development of innovative methodology for detection and location of repeating events and precise earthquake focal depths, enhanced induced events monitoring for major shale gas basins in BC and Alberta, and also media interviews, including live programs by CBC and local radio stations on significant induced events and induced events research. This slide gives a list of our project members from the Sydney office, Ottawa office, and Quebec. We also have contributions from scientists supported by external fundings, graduate students, contractors, and volunteers. This slide shows a list of collaboration highlights. First, we have multilateral collaboration on induced earthquake study. We signed a collaborative agreement with Ovintiv Canada to establish a dense seismic array to study the source process of hydraulic fracturing-induced earthquakes at unprecedented resolution. This experiment received funding from Innovation Solutions Canada for more than $400,000 and logistics supports from Samrock Incorporation and the BC Oil and Gas Commission. We also obtained external research resources from Geoscience BC for more than $154,000 in support of the routine operation of seismograph stations and injection-induced earthquakes research in Northeast British Columbia. We also have obtained support from BC Seismic Research Consortium for more than $135,000 in support of the injection-induced earthquake monitoring in the Western Canada Sedimentary Basin. We have enhanced the local and regional seismograph coverage of Western Canada with the coordinated effort from Canadian universities and international institutions, including McGill University, University of Victoria, University of Calgary, Ruhr University Bochum of Germany, Geoscience BC, BC Oil and Gas Commission, and the Canadian Association of Petroleum Producers. And finally, we have joined injection-induced earthquake research and publications with many universities and other research and regulator organizations. We develop innovative methods emphasizing on the application of AI-based algorithm to automatically and accurately locate a large number of small magnitude injection-induced earthquakes in BC, Alberta, and the Northwest Territories. Our induced earthquake catalogs are published as a series of Geological Survey of Canada open file reports, and they are freely available at NRCan's GeoScan database. We also provide the daily earthquake catalog to BC Oil and Gas Commission to help their regulatory decisions. During the year of 21 to 22, our project published a total of 13 peer-reviewed papers, all in internationally well-established journals. Some examples are shown in this slide. Specifically, we have papers published in Nature Communication, Nature Scientific Reports, Geophysical Research Letters, Journal of Physical Research Solid Earth, Seismological Research Letters, Journal of Petroleum Science and Engineering, and Bulletin of Seismological Society of America. I do not have time to explain all our research results in this talk. Instead, I would like to introduce the discovery that we reported in this particular Nature Communication article, which was published in late November 2021. In this study, we investigate the seismic activity in an area with many active hydraulic fracturing injection wells in northeast British Columbia. The location of our study area is marked on the map to the left. Each yellow circle represents the epicenter of one earthquake. The size of the symbol corresponds to the event's magnitude. Red stars correspond to events bigger than magnitude 4. The blue diamonds marks the location of hydraulic fracturing wells. After we carefully examine the seismic waveforms of the earthquakes that occurred close to the injection wells, we discovered that some events appears to have waveform characteristics that are very different from ordinary induced events. In the middle part, two such examples are shown side by side with typical induced events on the left and the anomalous event on the right. Generally speaking, given the same magnitude, we notice that these events appears to have broader P and S pulses. We also notice that they have much longer coda wave that arrived after the S phase comparing to the typical induced events. On the right, we show the spectrogram of the typical induced events on the top and the spectrogram of one of such events on the bottom. It is very clear that those anomalous events have a coda wave enriched in relatively low frequency content. We have conducted a series of thorough analysis to confirm that the observed waveform patterns are related to the source process of these events, which implies that they are probably a new type of injection-induced earthquakes. Based on our findings, we name this new type of injection-induced earthquakes as earthquakes characterized by hybrid frequency waveforms, or EHW in short. More detailed investigation into the source characteristics of the EHW events indicate that these events have generally lower stress drop and slower rupture speed. On the left, we plot the corner frequency versus seismic moment, and the slope correspond to the event's stress drop. Typical induced earthquakes have stress drop in the range of 1 to 100 megapascal, as indicated by these gray circles. In contrast, EHW events, their stress drop is generally below 1 megapascal, and sometimes can be as low as less than 0.1 megapascal. The rupture speed of a typical injection-induced earthquakes is about 2.35 kilometers per second. However, EHW events generally have much slower rupture speed, ranging from 2 kilometers per second to as low as 0.2 kilometers per second. We conclude that the EHW events probably manifest the slower rupture speed, slower rupture transitioning from aseismic to seismic slip caused by injections. Therefore, the observation of EHW can provide an effective way to assess the increasing likelihood of seismic rupture due to fluid injection. Ultimately, we hope that our discovery can lead to a better understanding of the seismogenic process of induced earthquakes that in turn would mitigate the seismic hazard from induced events. This is a list of our published papers and reports. And here is my contact information. Thank you very much for your attention.